talking about killed process. So tau A is the time of first exit from A. First exit from A. So Pn of A of x and y is just, it's the same thing, it's just we restricted to xn equal to y, we restricted to when n is still less than the exit time from A. And this is called heat kernel. But it is killed or let's say stopped, it's better word, stopped on exit from A. So PA of f of x is equal to y summation over all points in A of P A of x and y f of y mu of y. So I showed you that even for restriction, our operator difference is the same. So Laplacian is still like this. So it's the same things. So we have a very important lemma. So it's about the heat kernel of stopped processes. So Pn plus 1, same as usual, but we add A as well because we're restricted to the set A as well. So the lemma says that it is Pn of, first we go to Z, and then from Z, just one step you go to Y, and then mu of Z. So summation is over all vertices. And because we have restricted ourselves to set A, so it is restricted to A and then Pn of x and z, pz and y, so the same thing. So for the proof of this, the proof of this is very easy because you just write by definition that by definition mu y Pn plus 1 is equal to the probability that if we start from x and after n plus 1 step we hit y while we are still tau A is greater than n plus 1. What is this probability? I mean, when n is still less than the exit time. So we can just use, because it's just one step time, we can just rewrite this as z over v over all vertices and p xn plus 1. So same as usual, but you could sum it over all events that tau A is greater than n plus 1. But we conditioned on when in xn equal to z, tau A is greater than n times Pna x and z, mu z. And so we condition on the fact that still even at time step n, we are still less than the exit time. And this is the summation over A of the same thing. So from knowing that x and z is equal to px and z, so we have proved this lemma. But the lemma has another point that says we should prove that Pn plus 1 of x and y minus Pna of x and y, it's equal to delta of y, Pna x and y. We should also prove that Pna x and y is equal to Pna y and x, like a symmetric. And then also we should prove that Pna of x satisfies a discrete time heat kernel heat equation on A with zero boundary condition on the boundary. On the boundary of A. So the proof of these just follows from definition, and so they are very easy. So let's talk about the green functions. The green function. So the green function GA of x and y is just by definition summation over Pna x and y. So the green function is the summation over these heat kernels. And the number of hits by x on y, we call it local time of x at y. So local time, you see it in different places in probability theory. For example, local time of Brownian motion. There are several meanings, but here we are just focusing on the green function, and we call it ln of y. It means local time of x at y. So this is because if we are counting the number of hits by x. So we are just summing from n-0 to n-1 of 1 in its indicator function. So whenever xr is y, it is 1. So we are just counting the number of hits by x on y. So as you see, Ly of 0 is just 0. For example, we have a domain, and there are many different, so it is a walk, it's a random walk, and then sometimes it may go out, and after a time it may return to A. So going out, and after a time we return back to A. And so we can write the expectation of this local time. Tau A is that exit from A, is a time to exit from A. And this is summation over n of the probability that xn equal to y while tau A is greater than n. It means that n is still less than the exit time. And this is equal to Pna, just a definition of heat kernel. You can write it like this, still n from 0 to infinity. And this is called, because it is very important, we call it a green function. It has a name. We call it green function. So this is your green function. And if your graph is recurrent, then gx and y is infinity. There is an important theorem that we should always think about it. If A is a subset of your vertices, and gamma, which is has some vertices and some edges, it's a graph, we call it is transient. So if A is a subset of V, and we suppose that either this graph is transient or A is not the total vertices, it's just a subset of that. And then we should prove that GA x and y, which is the green function, is equal to, so the green function has a meaning. It means that the probability that time to hit y is less than tau a. GA y and y for any x and y in your vertices. So to prove the first part, which is this part, we just apply the strong Markov property of x at y. So all of us love strong Markov property because it's a tool to just say, oh, how can we define dependence and independence when you have a long time series. For example, if we apply strong Markov property of x at ty, it means that the probability that our x ty for any stopping time, for example, here our stopping time is ty. If it is jy, if tau plus m, here tau is y, tau ty is equal to jm, and our ty, our stopping time, is less than infinity, it is the same thing as saying that x1 equal to j1 and xm equal to jm. So if we are here, if we are jm, j2, j3, j4, jm, and then it goes out, and after that the probability of this event happens is the same if we start from the graph from the first time. So it means that if you increase the time, because we have a good stopping time, the probability is the same. So this event has the same probability from that event. So essentially it says that they are the same thing. And how do we just use this to prove that? We just apply strong Markov property at ty. So what we can write is, by definition, it is expectation of our local time. And from here, we just use the trick that we always use, Ey, Ly, L tau a. And then this is the probability if we start from x, time to hit y is less than tau a. And your green, but y and y, mu of y. So we have proved the first part. The second part of the lemma says that GA of y and y is times mu y is 1 over the probability that tau a is less than tau y plus. Plus means return to y, the time to return to y. So this is less than infinity, and we want to prove this. So again, we have y, and some of these random walks stays inside, but some of them goes out, for example, to a node z, and then from there it returns back to y. And this is a set A, for example. So if you imagine this set, we can write that if P is, let's call it the probability that T plus Y is less than tau A is less than 1. So this is clear from the definition, and if gamma is transient. So let's just focus on the case that your graph is recurrent. So what do you do when your graph is recurrent? That then there exists such z, this z outside. So there exists such a z outside of the set A, and therefore we can write the probability that ty plus greater than tau A is greater than equal to the probability that return to y is greater than time to hit z. And again, we are using the strong Markov property. So strong Markov property is very important because if you apply it for t of y, we can write that, so I just recall that you can write ty plus 1 equal to j1 and xty plus m equal to jm. So this technique, we use it for many proofs. To prove many theorems, we need this strong Markov property, and it's very easy. So that's why we love stopping times, because as soon as you find a stopping time, you can use this trick and see how a long series could be seen as a dependent or independent on other variables. So it's a way to deal with your filtration. So this is the proof, and then so graphically I should say that if this is A and we have Y, sometimes it takes this amount of time, sometimes it takes this amount of time, and there are some events that takes this amount of time. So we first hit Y. This is Y. We first hit Y, and then the second hit Y. So we should arrange it. So the first hit of Y, and then the second hit of Y, and then the case hit of Y, and then after that it goes out of A before it hits Y again. So by this graphical picture, now you understand that L tau A of Y has a geometric distribution. So summing the series in K, we can write mu y GA of y and y expectation of L tau A y, which is equal to K from 1 to infinity. So Kp K minus 1, for example, the case up until K minus 1's trial, it is, for example, you have failed, and after that you have win the game, for example. This is the way you think about geometric distribution. And even if you look at the Wikipedia, you will see that it's just the inverse of your probability. So you don't need to write this. And the probability of tau A is less than Ty plus. So this is less than infinity, and we have proved it. And now we want to talk about superharmonic functions in A. We call it superharmonic if delta F is less than equal to 0. Look at this inequality. We know that when it is equal, it is just harmonic. So when delta F is equal to 0, we call it is harmonic in A. So locally it is harmonic. And in terms of probability, we say PF is equal to F. And you know those terminology. So when delta F is less than 0, it means that PF is less than equal to, don't forget the equal one, because a superharmonic functions sometimes becomes harmonic, so it's less than equal. So you should pay attention to these inequality. Also, subharmonic in A, it